Hello friends, welcome to this lecture on computer aided power system analysis. In the last lecture, we have introduced the concept of a state estimation, and we have also started looking at the measurement model of a simple electric circuit. Today we will continue with that. So, what we did till last lecture is, we are essentially talking about weighted least square method. Now, why it is weighted least square method, we still did not explain. So, we should be explaining this in today's lecture. Now, what we have done in the last class, that we have considered a simple electric circuit, and in that simple electric circuit we have taken one voltage source and one current source, and there were several resistances connected in various combinations, and we said that the voltage source and the current source, they are unknown. So, we have treated them as the unknown quantities, or rather the state variables which we wanted to know, and for that we have also put 4 meters, some of them are ammeters and some of them are voltmeters, and then we said that these measurements, they can be expressed as a function of the state variables plus some error. So, what we did is, what we said that let this measurements we said now here. So, we said that Z 1, that H 11 x 1 plus H 12 x 2, and we said that it will also have some error which is unknown error, but which is random in nature. So, H 22 x 2 plus E 2, Z 3 is H 31 x 1 plus H 32 x 2 plus E 3, and Z 4 H 41 x 1 plus H 42 x 2 plus E 4. Now, here this Z vector, Z 1, Z 2, Z 3, Z 4 transpose. So, this is a 4 cross 1 vector. This we call as the measurement vector. Where these quantities Z 1, Z 2, Z 3, Z 4 are nothing but the measured values. X vector X is x 1, x 2 transpose. So, this is a 2 cross 1 vector, we call is that state vector. State vector. State vector is nothing but the vector comprising of the quantities which are to be determined, and we also denote error vector E as E 1, E 2, E 3, E 4 transpose. Again, this is a 4 cross 1 vector. So, we call it as an error vector. Now, as we said earlier, that our goal is to find out the values, or rather the estimate the values of x 1, x 2 such that the effect of these errors are minimized. So, then therefore, we need to derive some objective function or some kind of index which will essentially compute the net effect of all the errors. Now, there can be several indices. So, one such index could be that we take that this index f, we call it this index f. We can say that we would be simply taking the case where we are simply I is equal to 1 to m. Here m is the number of measurements. So, then here in this case we can say that f 1, that I mean one such measure could be that what we would be doing, that we would be simply add all these errors, and then basically what we are saying here is that we would be simply trying to minimize the sum total, or rather the algebraic sum total of these errors. So, our goal probably could be that we would like to estimate these values x 1 and x 2 such that the algebraic sum total of these errors would be minimized. Now, this looks elegant, but the problem is that it has got a very basic problem, that these values E 1, E 2, E 3, E 4, they, because they are essentially random in nature. So, then therefore, they can be either positive or negative. So, then therefore, if we take just their algebraic sum, so it may happen that they will cancel each other automatically. For example, suppose for example, say that E 1 is let us say some unit value, let us say 5 plus 5, this is the error. Let us say E 2 is let us say minus 3 some value, E 3 is let us say plus 3, and E 4 is let us say minus 5. So, then therefore, f 1 would be is equal to 0, E 1 plus E 2 plus E 3 plus E 4 would be 0, but the point is individually these errors are very high. So, then therefore, although their net effect, that is the net algebraic sum, would be 0, but individually because these errors are very high. So, then therefore, individually these measurements are extremely erroneous, So, then therefore, this measure cannot be used. Second measure could be, now we said, now here in this earlier case that particular problem arose because of this fact that we are taking the algebraic sum. Now, instead of that, suppose we take this, just the magnitude of them. So, then in that case obviously this problem of automatic cancellation of the errors will not be there, but the problem is that this particular function is not really very much differentiable in an elegant manner. So, then therefore, this particular measure, or rather this particular objective function can also not be used, because this quantity is not really very much differentiable, or rather it is quite difficult to work with this particular objective function when you have to do some kind of differentiation. So, then therefore, what we do is, what we use is something called, so to do this we use something called EI square. So, when we do use EI square, so then therefore, again this particular objective function also does not have the problem of automatic cancellation of the errors, and also this is also very much easily differentiable. Now, here in this case we have given equal weightage to each and every measurement, but depending on the accuracy of the meter, for example, M 1 could be let us say 1% error, that is basically this M 1, and M 2 could be let us say can have let us say plus minus 5% error, it can have let us say plus minus 1% error. M 3 could be have something called plus minus 3% error, and M 4 could be very erroneous, let us say plus minus 10% error. And this M 1, M 2, M 3, M 4, M 1, M 2, M 3, M 4 are the meters, So, then therefore, if we use this particular objective function, or rather this particular measure, what we are doing is we are actually giving equal weightage to a very accurate meter, that is M 1, or a very bad meter, that is M 4, and also to the other intermediate meters, which is not very fair. So, then therefore, what we do, that to give adequate weightage to the accuracy of the different meters, we do use some weight. So, we do use some weight. So, we call it WI square, where WI are the weight Wi is the weight of the, so it is weight of the ith measure, ith meter. So, weight of the ith meter. Now, obvious question comes that what should be the value of the weight? Well, now this issue we will come in little later, but right now let us understand, let us now accept this fact that for our estimation purpose we do use this particular measure or this particular objective function is the most appropriate, because it has got a very beautiful differentiable property and it also does not allow automatic cancellation of the error. So, now in our case, so then therefore, in this present case f 3 would be actually W 1 E 1 square plus W 2 E 2 square plus W 3 E 3 square W 4 E 4 square. Now, as we said, our objective is, in fact, now here I mean instead of saying f 3 we can simply write it as f. So, this mod, so now our measure is called f. So, this is the objective function f, or rather the measure. So, now as we said that we would like to estimate our state such that the net effect of the errors are is actually minimized, and we have developed some quantifiable measure that is given by this particular expression. So, then therefore, what we want to do now, we want to estimate these states x 1 and x 2 such that this quantity is minimized, because this particular quantity is essentially reflecting the net effect of the errors on the system. So, now because we wish to minimize this such that minimize their effect, so then therefore, it follows from simple differential calculus that del f 1 x 1 should be 0 and del f by del x 2 also should be 0, right. So, we are basically trying to minimize this function such that with respect to x 1 and x 2, that means that we are simply trying to estimate x 1 x 2 such that this particular effect of the errors is minimized. So, then therefore, if I now do this analysis, so now what do I get? I get that del f del x 1 is basically 2 W 1 E 1 del E 1 by del x 1 plus 2 W 2 E 2 del E 2 by del x 1 plus 2 W 3 E 3 del E 3 by del x 1 plus 2 W 4 E 4 del A 4 by del x 1, this should be 0. Similarly, del f del x 2 would be 2 W 1 E 1 del E 1 by del x 2 plus W 2 E 2 del E 2 by del x 2 plus W 3 E 3 del E 3 by del x 2 plus W 4 E 4 del E 4 by del x 2 is equal to 0. Now, if I take these two equations together and write them in a matrix form, so then what do I get? So, I get that so I get del E 1 So, we get something like this. Now, before doing this, we have to do something else. Now, what is del E1 del x1? Now, we have got Z11 is equal to H11 x1 plus H12 x2 plus E1, and Z2 is equal to H21 x1 plus H22 x2 plus E2. Z3 is equal to H31 x1 plus H32 x2 plus E3. Z4 is equal to H41 x1 plus H42 x2 plus E4. So, then therefore, if I do del E1 del x1, what I will get? I will get minus H11, and similarly del E2 del x1 would be minus H21, del E3 del x1 would be minus H31, del E4 del x1 would be minus H41, del E1 del E1 by del x2 would be minus H12, and del E2 by del x2 would be minus H22, del E2 by del x3 would be minus H32, and del E2 by del x4 is equal to minus H42. So, then therefore, if I now substitute this, so then what equation I get? Now, if I now substitute all this in this, so we get an equation that del E1 x1 is H11, del E2 x1 is H21, H31, H41. So, we get that W1 E1 H11 plus W2 E2 H21 plus W3 E3 H31 plus W4 E4 H41 is equal to 0. And similarly, if I substitute del E1 by del x2 and etcetera, I mean these 4 into this, so we get that W1 E1 H12 plus W2 E2 H22 plus W3 E3 H32 plus W4 E4 H42 is equal to 0. So, this is what we get. Now, we need to put them in a matrix form. So, put them in a matrix form. If I wish to put them in a matrix form, so then what do I get? So, first we write is simple is that, but we write is W1, W2, W3, W4. So, this is a diagonal matrix. So, this is a diagonal matrix, this is all 0. So, this is a 4 cross 4 matrix. Then we have here E1, E2, E3, E4. So, if I now this is also a 4 cross 1 matrix. So, now if I multiply this, I would get W1 E1, W2 E2, W3 E3 and W4 E4. So, this is 4 cross 1. So, then therefore, what I will get is H11, H21, H31, H41 and H12, H22, H32, H42 is equal to 0, and this is a 2 cross 4 matrix. So, then therefore, if I do everything, so I will get this equation. So, obviously, this is this and this is W 1 E 1 plus W. So, this and this would be W 1 E 1, W 2 E 2, W 3 E 3, W 4 E 4. So, the first row would be H 1 1 into W 1 E H 2 1, W 2 E 2, H 3 1, W 3 E 3 plus H 4 1, W 4 E 4, and similarly the second row we will get. So, now this matrix we denote as the capital W matrix. This is in capital W matrix. So, this is the wet matrix, we call it as wet matrix. This is the wet matrix, and this is the vector. We have already seen that this we denote as a vector E. Now, in this expression, now if I do take this expression can be written as vector Z is equal to sum matrix H into vector X plus vector E, where this matrix H is H 1 1, H 1 2, H 2 1, H 2 2, H 3 1, H 3 2, H 4 1, H 4 2. So, this would be a 4 cross 2 matrix. So, if I write these 4 equations in a matrix form, I get that Z is equal to sum matrix H into X bar plus E bar. X bar is the state vector, E bar is the error vector, Z is the measurement vector, and H is the matrix, connecting matrix, and this is an 4 cross 2 matrix, and H would be as H is H 1 1, H 1 2, H 2 1, H 2 2, H 3 1, H 3 2, and H 4 1, H 4 2. So, then therefore, if I say that this is equation 1, so then equation 1 can be written as H transpose W into E is equal to 0, right. H transpose W into E is equal to 0. Now, from this E is equal to nothing but Z minus H x. So, then therefore, now H transpose W and E is Z minus H x is equal to 0. So, then therefore, I can write down that H transpose W Z, Z is the measurement vector, is equal to H transpose W H x. So, then therefore, I do write that x is equal to H transpose W H inverse into H transpose W Z. So, this is the estimated value of the estimated state vector. Now, we denote G, that is we denote that G is, we call it gain matrix, is H W W H. So, then therefore, estimated state vector we with an hat. So, this is an x bar hat, hat stands for the estimated state vector. So, we write it as G inverse H transpose W Z. So, this is the final expression of the estimated value. Now, why do we really call it a weighted least square method? So, now let us look at this. What we have done? We have actually, our measure is this is our measure, and what is this measure? We are first squaring the errors, and then we are multiplying the squared errors by their weight, and then we are minimizing this resulting function. So, then therefore, this is actually, this function is nothing but this function basically give the weighted square error. So, this function is nothing but it gives is the weighted square error, right. Because this function gives weighted square error, and we are trying to find out this estimated state by minimizing this particular weighted square error. So, that means we are simply trying to minimize, or rather we are simply trying to make this particular function, or rather this weighted square error as the least value. So, then therefore, this is called weighted least square method. So, what we are essentially trying to do? We are trying to find out the estimated vectors by such that the weighted square error is the least. So, then therefore, and that is precisely why it is called the weighted least square method. So, we write that this as the weighted square error is made least for estimating the state vector. This vector is called weighted least square, or WLS technique. So, now here x again let us look at that it is G inverse H transpose W Z. Now, let us look at the general case. G is given by H transpose W H, H transpose W H. Now, let my in a most general case X, that is my unknown vector, is an n cross 1, that is there are total n number of quantities to be estimated. Z is an m cross 1, that is there are total number of measurements is m. So, then therefore, E also would be m cross 1, and W would be, that is the weight matrix, would be an m cross m matrix. So, then therefore, what would be H? H would be an m cross n matrix, mth row n column. So, then therefore, what would be G? This is H transpose, so it is n cross m, W is m cross m, and this is H is m cross n m cross n. So, then therefore, what would be G? So, then therefore, G would be n cross m cross m cross n. So, G would be n cross n. So, it would be always a square matrix, always a square matrix. So, here in this case what would be G? In our case what would be G? In our case G would be basically 2 cross 2. So, in our case G would be, here G is 2 cross 2, here G is 2 cross 2. So, then therefore, what would be the x vector dimension? It is n cross n, H transpose is n cross m, that is H transpose, W is m cross m, and Z is m cross 1. So, then it ultimately x is n cross 1. So, n cross n, so n cross m, n cross m, m cross, so it is n cross 1, what it should be. So, therefore, we have obtained the expression of the estimated values of the state vectors by minimizing the weighted squared error. So, essentially we finish today now. In the next lecture, we will be continuing to see the other aspects of this particular method. Thank you.